So who we are and what are we doing? We are in a physical chemistry course. We hope to complete everything related to harmonic oscillator today, but do not dream of forgetting about oscillator. We will come to it again and again because a lot of things oscillate, not only oscillators. By the way, in the homeworks, by some reason, I'm fine with grades. We all should be happy, but you did mention like 2 or 3 examples. There should be like at least 5 examples of oscillator. Right? And if the majority of us, of you, are chemists, main example of oscillator is interatomic distances, vibrating molecules, infrared spectroscopy or Raman spectroscopy. Raman, give me a sign if you didn't hear about it. Give me a sign if you did hear about it. Okay, so electronic excitation between different electronic levels, optically by like yellow quantum. Yellow. Up and down. And each excited state has different potential surfaces. And if it is harmonic, there are like levels. And if you tune and make it offset excitation, a little higher than main frequency, a little lower than main frequency, it can go not from the ground vibrational to ground vibrational in ground excited electronic, but it comes from ground electronic lower vibrational excited electronic. I don't want to excited electronic and excited vibrational. Or it can go otherwise, ground electronic excited vibrational to excited electronic ground vibrational. And then the overall frequency will be offset by few h bar omega, where omega is vibrational frequency. So this technique allows to measure vibrational properties of such normal modes, and I will ask if you have heard the word normal modes, which are not active in the infrared irradiation, in the regular FTIR devices. Okay, normal modes, give me a sign if you have heard, give me a sign if you didn't hear. Okay, I was planning to goof up and not tell about it, because it is boring, but it is, I was just choking this out. The normal modes, it is a primary goal of the physical chemistry course. I was trying to avoid it, but okay, there will be no time to do everything in details what I've planned, so at least I tell this. If you have H2 mode, there is only one vibration. But if you have H2O, how many vibrations do you have? Each hydrogen can vibrate towards oxygen,
and sway,
and then they can play rapid. So there is an equation like 3n minus 6. Yes?
for nonlinear.
So if you have 3 atoms, times 3 will be 9, minus 6 will be 3. Therefore, 3 types of vibrations. So if you have so many atoms, each of them can vibrate, and total number of vibrations is huge. But the concept of normal modes is that a lot of atoms are similar. Most of us consist of carbons. And carbon distance have a very similar frequency. So many modes mean that a lot of carbons coherently move simultaneously with the same frequency. But they should be a little bit different, and they may have a little offset of frequency, and they have a little offset of type of vibration they control. So specific type of vibration with specific frequency and specific vibrational eigenstate is called normal mode. Okay, I am done with my details. It was main goal of the physical chemistry course in general sense. But let's go to, more deeper into harmonic oscillator, which we should complete now. Which ways to predict future do we know? Do not answer, just tell many. Right? And we know time evolution operator, we know expansion over eigenstate Schrödinger equation, and there is one thing that we didn't give enough attention, but it is a so-called Heisenberg equation of motion. I'm not done with the list of projects, but here I put in the lecture the stuff that I failed to distribute last time. So it is general ideas how to organize your effort towards completion project. So we learned coherent states, we learned how the amplitude of coherent state accumulate phase, and we learned that if you represent the unit state in Cartesian space, it will be Gaussian shape that goes forth and back with constant shape in width. Good methods. But here there is a Heisenberg equation of motion, which means a tool to reduce number of degrees of freedom. And if really someone wants us to do calculations without computer or more elegant than computer, and we have to replace computerized modeling and true experiment by pen and paper, we need to seek any opportunity to avoid many degrees of freedom and try to concentrate on a few. And Heisenberg equation, the equation of motion is the way to practically reduce number of degrees of freedom in the calculations. So if we are looking on a specific observable, expectation value of a specific observable, we can write down an equation of motion for such observable and forget about the rest of the quantum features of the system. Very often it is possible. So, whatever time we have, this is the last slide I want to arrive at. So, we are going to come to the idea that oscillator oscillates. Again, I know it is not very exciting, but we are going to get this a little trivial answer from different angles to be absolutely sure that oscillator always oscillates. You know, you are doing homework 6 or even homework 5, coupled set of equations for position and momentum, classical. Remember? Something like this. So if you're trying to set up an equation of motion for position only in this oscillator, it doesn't couple to itself to a position. And if you remember classical physics, typically there is connection to velocity or acceleration. I'm not telling anything precise, I'm just showing general directions. So if you want to predict future in sense of classical mechanics, you need to know current position and you need to know the velocity. Right? Depending on where your velocity, where the particle is kicked, direction of velocity, the absolute value of velocity, the trajectory will be different. And when for 1 degree of freedom we keep track of position and velocity, we can call it phase space. For each particle, 2 variables. Position and momentum. Phase space. So when we launch something to oscillate harmonically, the position or the thing that changes harmonically as position, which could be position of cloud, collective cloud of electrons and plasmons, which could be displacement from equilibrium in the normal mode, which could be strength of electric field in the LC contour of your cell phone. Cell phones were written by everyone. Everyone now recognizes that cell phones do have something oscillating inside, and I'm so happy. So at least I see a feedback that what I'm telling, even if you're not taking notes, something is getting recorded. Yes, there are oscillators in cell phones. So things that oscillate goes from equilibrium to maximum to minimum harmonic. But at the same time, there is a derivative of this main variable, velocity, momentum. When you have maximal displacement from equilibrium for given energy, the velocity is zero, momentum is zero. When it starts going back, the position decreases and momentum increases. Increase. When position is zero, momentum is maximum. And then when it goes to opposite side, it starts to feel like not friction, but force acting on from the opposite side. So it goes further, but velocity, momentum gets smaller, and then it arrives at turning point. Elongation is maximum, but with negative sign. Then it turns and starts going back, and momentum was zero, and then it starts taking negative values. So if you make it as a parametric plot with two variables, and if you are quantum, it will be not taking position, and expectation value of position. Then for this harmonic motion of harmonic oscillator, this phase-space trajectory will have the shape of a circle. Okay? This is trivial. You may have seen it in high school in differential equations, because it is one of the simplest differential equations to solve. You may have seen it in classical mechanics if you were taking physics. In some of the chemical kinetics reactions, there are some cyclic reactions where you may have seen this. But many things do oscillate. So it's, to some sense, it is more mathematical problem. What else in the list of oscillating things? Oh, strengths of electric field between the resonators in the laser. This is one of the coolest oscillators in the universe, at least for people dealing with science. So, if we want to follow these single observables, why don't we set up equations of motions for them? But you may have recorded your profile of this course that you never go in a straightforward way. There will be some complications and crazy bypasses. And I will try to convince you that these bypasses are quick. So instead of doing equation of motion for position and momentum, we will do equation of motion for expectation values of annihilation and creation operators. But they are connected to position and momentum as a linear combination, both for operators and expectation values. And you have practiced this connection in the homeworks, right? Right now it is not a big surprise. You see why we are trying to set up homeworks a little ahead of time. So I saved my time on the stage. So we will set up, solve equation of motion for expectation value of position, expectation value of annihilation and creation operator. Solve them really easy. It is practice of least action in life. So it is one of the simplest differential equations to solve. And then we will just add or subtract them to construct position and momentum with appropriate coefficients and get this figure. Since we are short in time, I will write minimal amount. You are like, as I see, you are not writing much, so you will just go through slides and listen to comments. If you're writing, it is really great. It will help you in the future. And if you're interested, I have scanned copies of lecture notes from similar course from like years ago students. Someone is in? Sure. Okay. Equation of motion for expectation value, which you can put here x, b, a, or a dagger. But always when we do it, we do commutation is Hamiltonian. So if our choices are annihilation and creation operators, we need to set up Hamiltonian and these operators in a such form that we can find the commutation. Yes.
I used to know the answer to this, but when do you need to tack on the partial derivative with respect to time on that equation?
When your Hamiltonian is time dependent.
Oh,
We are trying to avoid it as much as possible. Since from last lab session, you were trying practically to check time-dependent Hamiltonian, and in the list of desired projects, Austin also mentioned as a possibility to check the Hamiltonian with time-dependent Hamiltonian. You are the only two who would go away from this equation and with an additional term. But most of us do not need it, and life is complicated enough without it. So, this equation doesn't surprise you. From given eigenstate, you come up for elevated eigenstate, or you go for lower eigenstate, which is the main concept of this equation and initiation. Before we go to computation of those operators with Hamiltonian, we may want to check how they commute with each other. And you will also know the answer because you have completed success. You have successfully completed all of the homeworks, and it was one of the assignments. I kind of skipped this part in the answer key, but now it is time. So how do they commute? We need to make product of these two operators in direct and inverse form, and then subtract, right? And likely you have already done it. So we have two summations: the one that annihilates, the one that creates. Then Brian and Cat meet each other. Then they are considered as a delta function. A snake eats the mouse. And we combine the factors in front. So when the little thing with plus goes first, we can see that it goes to the operator, which has only diagonal elements if you represent it as a matrix, and the factor is proportional to the index of the state. Some people also call it number operator, because the higher the number of excitation, the higher is the numbers. So number of vibrational quality in the system. If we do empty spots, or meaning that I was planning to derive, now I'm kind of practicing with action. So inverse time. So first going from given out of up, and then going out of down. Again, merge this Brian Cat, convert them into delta function, which demands us to set up that m is equal to n plus 1. And through this delta function, we eliminate one of the summations. And when we carefully process it, we are getting same style of operator, which is 0 everywhere except diagonal. But the factors on the diagonal are always bigger by 1. So it is just silly algebra. If you perform this exercise, the order of operators, change swap of the order of operators adds, increases the factor by 1 at each point. What will we get if we use, yes?
Just out of curiosity, and it might be in the Brian Cat stuff that I'm not seeing, but why do you cancel out the summation of m and not the summation of n?
Which summation index to eliminate? It doesn't matter. They all, I will take a lesson of English from this. Before the cinematography got a soundtrack, when there was a Charlie Chaplin, what was the name for the cinematography?
Silent films.
Silent films. So those are silent indices.
Okay.
Because there is summation of them, and whatever you can replace it to any letter. If you make summation over it, silent index. So you can make summation over another one. And then you just rename indices in the different order. Instead of n equals m minus 1, you can tell that m equals n plus 1. See, it's equivalent.
Okay.
So it's a frivolous choice which doesn't change the answer.
Okay.
Okay? And if you subtract these two things, then the answer will be a diagonal matrix with 1, 1, 1, 1, 1 on the diagonal, right? No objection. See, I'm frivolously changing the letter and do not care, do not worry about it. So k plus 1 minus k equals 1. It's a big discovery. So this is, okay, the image is covered here, but I just sketched the matrix which has 1, 1, 1, 1, 1, 0, 0s. So it's identity operator. So it is a matrix which change nothing. Good? Who we are, what we are doing, where we are. I'm repeating, maybe you good enough coffee that you are clearly following what is going on. I'm recalling it for myself. So we are describing oscillating oscillator. We are focusing on the expectation values of position and momentum, how they evolve in time. Since we know that they are linear combinations of creation and annihilation, we are solving Heisenberg equation of motion for expectation values of annihilation and creation operators. Since Heisenberg equation of motion involves commutation of our operators of interest with Hamiltonian, we are getting through a lot of operator algebra for these operators. So our next step is to find commutation of this annihilation equation with Hamiltonian. Okay, this is where we are now. Okay, well, this is true. This is something that energies of different levels of harmonic oscillator, it is something that you need to memorize, that what will be needed in other courses. General mumbling about Raman and normal modes also something that you need in other courses. This, do not memorize it if you are not interested in theory. But until the end of the course, maybe you may come up to those equations again. And if you ever need to take something quantum. Okay, so here is the number operator plus 1/2 times frequency Hamiltonian, and then we need to find co-mutation of annihilation of Hamiltonian and creation with Hamiltonian. You just completed the homework. You completed it way ahead. I just returned to those who found time to come. Some of you probably, by lack of time, skipped this exercise, but now you have a chance to see the answer. So, if we replace A without dagger to A with dagger, as a price, you change the sign in front. In your homework, you had opposite order, A dagger H, and then you had minus sign as well. Because by definition of commutation, if you commute the same operators but you swap the order, as a price you get minus change of the sign, right? Okay. There are no challenges anymore. And there is no much time anymore. So, as soon as you know these commutations, you can plug them into Heisenberg equation of motion immediately and get the answers. So in Heisenberg equation of motion, you do not have minus, it is plus. And we are thinking about expectation values. We always think about this stuff. But the equations will stay non-changed even if you do not write this with angular brackets. And some people can think of operator changing in time. It's a little dangerous for the brain sanity. With bracket, it's much easier to intuitively perceive what is going on. But mathematically, it doesn't matter. So plug in the value of commutation, so negative sign, and the annihilation itself. So what previous slides show commutation of annihilation is Hamiltonian gives annihilation again, right? With minus sign. It is one of the simplest differential equation one can imagine. So derivative of the unknown over free variable gives unknown. Right? This is a level of complexity I like. You shouldn't go to anything more complicated. So if you divide everything by a, you have differential unknown over unknown, which upon integration will give logarithm. And here you have just integral of constant, which will linearly grow, right? Well, the constant is imaginary, but who cares? And then, so we get logarithm of annihilation equals constant times t. And if we place this stuff to the power of exponential, on the right you get our favorite and main thing that comes back to us everywhere in the quantum course. Complex accumulation of phase. Right? And on the right, exponential of logarithm will be a. And if you want to be rigorous, then we need to place initial condition here, which can be operator, or if we are talking about expectation value, at time 0. So I need to keep our mental sanity. So expectation value of annihilation operator at time t will be whatever we got at time 0 times accumulated phase. Well, times exponential to the power of accumulated phase, right? So it means that on complex plane, if you keep the same radius and goes real imaginary, just so. Any logical connections to material in the past? Coherent state, which is eigenstate of annihilation operator, is a superposition of all eigenstates with different powers of this parameter of eigenvalue of annihilation operator, which is time dependent, which accumulates phase. So before we got the thing through practicing Taylor expansion of exponential. And I remember that not many of you were aware of this Taylor expansion. Hopefully now everyone is. But now we are getting the same answer. This is what we call mu, or later on gamma, to follow British scientists. So expectation value of annihilation operator just accumulates complex phase. If you do the same thing for creation operator, the story repeats with positive sign. Plus here, and then a dagger equal, well, again, I do not want us to go crazy. This helps a lot. So expectation value of a dagger is equal to what was in times 0 times exponential with plus I omega t. So it also accumulates phase, but different way, which can be interpreted as evolution backwards in time, right? If you change t to minus t, you'll get the same as here. So we got two things, and now there is we need to construct position and momentum out of expectation values of creation and initiation. For position, you add them. For momentum, you subtract them. And I have seen that many of you have successfully completed this. Therefore, I can take vacation and not show equation for momentum. So, what do? We plug in solutions for time evolution of this expectation of creation and annihilation, which is their initial value and this phase accumulation. Good. What are their initial values? If we want to establish bridge from this boring theories and more or less real life. If you know position at time 0, if you know momentum at time 0, then we know annihilation at time 0. Right? So we are plugging this one in here and this one into there. Okay? And then we have on the input, we have initial value of position, initial value of momentum. On the output, we have time-dependent position and time-dependent momentum. Right? What is a little counterintuitive and surprising? Nothing. If you are practicing classical mechanics, but if we are seeing these equations for the first time, I have a little. When I saw equations like this for the first time, I had a little confusion. Here, we do have P at time 0. And here we have expectation value of position. So, if you think carefully, then it is not a surprise, but it is an interesting observation. The trajectory of position explicitly depends on the choice of initial momentum. In some sense, if you, for example, you can start with no elongation, but with a kick, with non-zero momentum. Or you can start with zero momentum and big elongation. Or you can have 50-50. So for a given energy, a fixed energy, for the same trajectory, you can start at different points of this trajectory. So you can, by selecting proportions between initial position and momentum, you can select initial phase. Therefore, momentum enters this equation. And similar things can be done for so, see, position momentum for dagger, position momentum for no dagger. And then you just process all constants and algebra, and you identify that when you get first and third term, they combine this oscillatory exponentials oscillating opposite sides with plus sign, which comes to cosine due to our old body Euler. And then for the second and fourth term, the exponentials rotating opposite direction come with minus sign and imaginary stuff, imaginary factor. And then, again, due to the old body Euler, we get sign. So careful processing. Luckily, we do not have time to do it. Otherwise, I would consider it as my duty to carefully write it down, and it would take at least half an hour. So then if you take care of all factors and conversion from complex plane to real, then you'll see that for the position, you get initial positions times cosine omega t plus initial momentum times sine omega t. So momentum explicitly enters. So even if initial position is 0, you still will have oscillations. And here is a little bit more on the factors. Initial momentum, initial position, both enter into trajectory for position. And I have an idea for next year to give this part also as a homework. Then I have to do nothing in the lectures. So for momentum and for position, you can formulate the answer as, so there is nothing serious here. It is just a way to record, to avoid much writing and to record the answer. So if we have a vector of initial values, x naught and p naught, and you have a vector of time-dependent answer, we can convert from these two parameters into this answer by matrix multiplication, or this matrix include all time evolution. So it is matrix that converts initial or past for position and momentum to the future of position and momentum. Instead of writing two equations, we can write one matrix equation. So this oscillations with frequency omega is, in some sense, it is, it's not formal, but kind of evolution matrix for phase space. I do not see why you will not see it in your future life, but I'm seeing these equations only while lecture, so do not bother memorizing. Maybe just general features. If we play with this expression, if you put it into, let's say, MATLAB or some other nucleus or origin, and set up fixed value for mass and frequency and initial values, and plotted this two variables, parametric plot of two variables, x and p. This will give you which shape?
Circle?
Yes. It's not a big surprise because we already discussed it. So when one variable changes as cosine, another variable changes as sine, then their parametric plot is given circle, right? And we think that I was always failing to memorize, does it go clockwise or counterclockwise?
Counterclockwise.
Why? Because when position decreases, momentum increases. So you just, if you elongate it and release it, the velocity is 0 and then it accelerates. It accelerates in the backwards direction. So you take a sling and you pull it one way, and then the velocity comes to the opposite direction. Lecturing is done, but I'm happy to answer questions.
Yes. Could you go back to that last slide?
Yes?
I think it would be.
I guess I do have a question.
Please.
If we are considering it to start at, you know, x not essentially, let's say, so x of 0.
Well, you can start at any, if you fix the energy, you can start at any point.
Okay.
Okay? And you will get the same trajectory. You can start with no elongation, but maximal velocity.
Okay.
Yes?
Are we sure that it's counterclockwise?
We're of the opinion that it should be clockwise.
if you pull it toward positive x and release it, the velocity vector is
It's going to go
opposite.
negative.
So it should be negative initially.
What happens if you pull it towards the negative x and release it towards positive x?
Then the momentum's going to want to go positive, right? It's going to come out of that getting more positive if it's negative. If the position's negative. Right? As if, okay, so
Yes.
if you have really high momentum.
I don't know.